the last application of integration in section or in chapter 6 is finding the average value of a function. It's also the easiest application. Really, all you need to do is know the formula and plug and chug. So I'm just going to put up the formula for you. Average value of a function f of x on an interval AB is given by taking the integral from A to B and then just dividing by the length of the interval. So it's really easy. Let me go through a quick explanation of why this holds. So what we're trying to do when we're trying to come up with this formula says we have, okay, some function like this. Say here's A and here's B. And we're looking for the average of all these values, right? So in some sense, that's fine. That makes sense. Sorry, it's not straight. Well, it's straight. It's just not horizontal. Doesn't matter. But the problem is that you have an infinite number of values, right? So usually when we take an average, you add up all the numbers and you divide by the number of things that you're averaging. But here, we've got this whole interval, so there's an infinite number of numbers, right? So we can't really exactly be like, oh, we'll divide by infinity. So what we're going to do is use the same kinds of ideas that we've been using with calculus this whole time. We're going to take this interval from A to B, and we're going to divide it up into n subintervals, right? So we have n subintervals of length delta x, right? So delta x is b minus a over n like usual. So we're taking the same subintervals. And then on each of these intervals, you're going to take one of these values of f, and we're just going to average those. Okay? So that's going to be not the exact average, right? But it's going to be some approximation. So I might be saying that f average is going to be approximately the average of those n values of f. Right? And then this is an average, so I have to divide by the number of points. Fine. I want to take this number of points to infinity, but then I've got, okay, well, now I've got an infinity in the bottom, so I know that can't be good, right? So what I want to do is get rid of this n. If I look at this, I can just take this little bit about delta x and solve that for n, right? So this would tell me that n is b minus a over delta x. So I can substitute that in for this n. I'm cheating, not writing the whole thing over because it's kind of long. This is b minus a over delta x. Now I have something that's a little awkward because it's a compound fraction. But hey, I can just multiply by the reciprocal. Right? F of x n star. So dividing by b minus a over delta x, and my thing's in the way here, is going to be the same as multiplying by delta x over b minus a. Right? And now I have something which looks like a sum, so I can write it with summation notation. So I'm going to put it down here. I'm going to write summation I equals 1 to n of f of xi star delta x over b minus a. But I actually don't like the way that looks, right? So I'm going to take out the 1 over b minus a. And then I'm going to write this guy in here. This nice looking Riemann sum. We know what's going to happen to that. Because what I really want to do is I want to take the limit of this as n goes to infinity. And I kind of wrote 2 steps in one there because I want to take the limit of the whole thing. But I can pull the b minus a, 1 over b minus a out because there's no n's in this. So the limit doesn't even see that. I just pull that straight out, right? So what I have here then is precisely once I take the limit, right? Once I take the limit, I have what I want. This becomes the Riemann integral, and that's my formula, the same one I have up there. So that's how that goes. You don't need to know that, like you don't need to reproduce that or anything. It's just kind of to know sort of where it comes from, and it helps us see what's really meant by the average value of the function. So I do want to do at least one quick example. They are pretty quick because you're just doing an integral, so it is not too bad at all. I'm going to erase this explanation, and I'm going to just leave up this. And the example problem that you might be asked to do would be something like this. They'll have to give you the f. They'll give you some function on an interval. So they give you that stuff. And then you just go ahead and you do the integral, right? In this case, it's not an area, right? It's an average value. It could be 0. It could be negative. It could be positive. So there's no little trick there that you can say, oh, that doesn't make sense. But one thing you can always do is graph it and see if graphically it makes sense, that it kind of looks like you have the same amount of stuff over and under where that f average is. So let's see. Oops, I wanted to write in what it was. Cosine to the 4th x sine x dx. So this is a pretty straightforward u substitution, right? We just do u equals cosine of x. Now, the derivative of cosine is negative sine. So I do end up getting a minus from my u substitution. So I have this. And I can change the limits, or I can just go back. I think I'm just going to go back today. Okay? When I integrate this, clearly I'm going to get 1 minus 1 over pi and u to the 5 over 5. That's a 5. Evaluate it at your limits, but I didn't change them, so I have to go back and put in what u is, which would be cosine to the 5th x. And now my limits, I can use my original limits, 0 to pi. So I have minus 1 over 5 pi, negative 1, minus 1. So I eventually have 2 over 5 pi. Okay. So there it is. This is very straightforward.